Okay, hello. How are you doing? We are going to be preparing ourselves for the quiz number 2. Okay, so I post a practice quiz for you and later today, and give you the list of assignments that we hope to be able to do it by the end of the week, by the quiz day. I extended, a little bit more the days for your assignment to make sure you are prepared for it. We hope to be able to give you the quiz up to the section 4.4 because these terms are interconnected to each other. You know that the quiz is going to be kind of take-home quiz. As usual, I posted over the weekend, then I give you the time to get it back to me. We talk about, we are going to continue. The idea was we consider special sets of vectors, linearly dependent, independent, and basically a set of vectors is going to be linearly dependent if any vector or one vector can be written as a linear combination of the other one. If this situation is not going to be possible, then we have linearly independent sets of vectors. So I show you how we're going to do it. Those practical examples that I gave you the other day was the list that you need to know. Now I'm going to put some results together, okay, some remarks, some results that are going to be useful, give us a better understanding of the system. And then there is one class of vectors of class of differentiable functions that's going to be very much related to this concept. And in case you want, or you've already got, takes the course differential equation, then you will see this one in that course. But we would like to connect it to here and explain it for you, okay? And so we did the practical games the other day, the examples. So that's some theorems that will help us, okay, first. Then I get to that calculus part to finish this, this section for you. So these are the type of problems that you need to do for us. Okay, as soon as you check your practice quiz or the assignment, mostly are going to be of this category. So we don't want you to miss anything and know how to do the problems for us. Okay, so these are the practical one that we did. How we went to check. We gave you 4 examples. Okay, class of just vectors in R3, R2, Rn. Then the vectors in polynomials, okay, polynomials of a degree at most n, and the matrices. So we're just going around these type of examples. So let's have some theorems, some results. They are, I'm going just to list those important ones. You can check the book if you want to need more. They are obvious results or the properties that we can have for these type of sets. Okay, so this first one is basically the one that we talk about it. If you have a set of linearly dependent vectors, so you can write any vector as a linear combination of the others, okay? So it's obvious result, but we are going to list it a set. Okay, this is it, a set consisting 2 or more. Okay, a set consisting 2 or more vectors in a vector space. In a vector space. Okay, V, if you like, is going to be linearly dependent. Is going to be linearly dependent. Okay, dependent if and only if, as we talk about it, it's going to be possible to write one as a linear combination of the other one. If and only if it is possible. Okay, it's going to be possible to express one of the vectors in terms of the other ones, okay, as a linear combination, linear combination of other vectors, okay, vectors. This is just a definition of the linearly dependent, okay? It's very easy to prove if you like, okay? So I just give you a hint for the proof if you like to see what type of, how we are going to operate. You see, for example, suppose, okay, that give an idea sometimes you want to prove some problems that we're going to have, so to get how we're going to operate. So suppose V1, V2 up to the Vn, for example, is linearly dependent. Linearly dependent. You know what does it mean? This means that there is, okay, there is scalars. So this means there exists, okay, there exists a scalar. Remember, a scalar is V1, V2, sorry, a scalar is C1, C2 up to the Cn, not all zero. At least one of them is not zero, not all, okay, not all zero, such that, what's that? C1 V1 plus C2 V2 up to the Cn Vn is going to be equal to the zero. Okay, so we know that at least one of them is not zero. Suppose that one is C1. Okay, for example, any. Suppose C1 is not equal to zero. If C1 is not equal to zero, so solve for V1 and then you're done. So that's going to be C1 V1 is equal to the negative C2 V2, okay, minus C3 V3 up to the Cn Vn. Since C1 is not equal to the zero, you can solve for V1. So the V1 would be what? Negative C2 over C1, V2 minus C3 over C1, V3, etc. minus Cn over C1, Vn. That's it. So this basically means what? This means V1 is the linear combination. So this means V1 is a linear, okay, combination of the others of V2, V3 up to the Vn. So if the vectors are going to be linearly dependent, means this is it, linear dependent. So this means one of the vectors is going to be linear combination of the other one. Okay, because at least one of them is going to be non-zero. So when you want to check, you see if this is given to you, want to see if it's going to be linearly dependent, you can have a look. If you can get one of them to be linear combination of the others, you're done. Okay, so the other way around is much easier. This means if one of these vectors is going to be linear combination of the other ones. You see, suppose, just pick one. Okay, suppose V1, if you like. Suppose V1 is equal to the linear combination of the other one. Okay, you may call it, D2, a scalar, V2, D3, V3, etc. up to the Dn, Vn. Okay, remember you want to prove that all the vectors are going to be linearly dependent. So move them to one side like the one that we did over there, okay? So this would be what? This would be V1, if you like, 1 times V1 minus D2 V2 minus D3 V3 up to the negative Dn Vn equal to the 0. There you are. You see, you have the V1, V2 to the Vn, all of them are 0. And one of the variables, one of the scalars, your scalars over here, 1 is not equal to the 0. You know that. If you have this linear combination in which not all the coefficients are 0, in that case, the vectors are going to be linearly dependent. Okay, so this means I just give you note that, okay, note that not all CIs, if you like, are equal to the 0. So that's it. So these vectors v1, v2, up to the vn is going to be, is linearly dependent. Linearly dependent. Okay, so that's it. That's a nice result. It's just you can use this one as a definition of the linearly dependent vectors, okay, or you just the one that we talk about it before, the C1 V1, but as C2 V2 to the C and Vn, okay. So that is a natural result and easy proof. So that's going to be one case, okay. This next one is very interesting and very useful. We're going to use it. If they give you a set of two vectors, if one of them is a multiple of the other one, these two vectors are linearly dependent. This is very useful and we're going to use it quite a lot. Okay, so the theorem, again, very easy to prove. Okay, and so that this theorem would define, or we are going to use it, linear, when we want to check the linear dependence. Okay, linear dependence of a set of two vectors only, okay, v1 and v2. And there are quite a lot of problems. We are going to have it. Okay, this is it. If v1 and v2 are going to be linearly, okay, are going to be linearly dependent if one of them is a multiple of the other. If one of them is not the multiple of the other one, they are linearly independent. Because we talk about it, you see, we talk about it that if a set of vectors are going to be linearly dependent, and this means one of them is a linear combination of the other one. So V1 to be linear combination of V2 is just a multiple of V2, okay? So the set of vectors V1 comma V2, okay, is linearly dependent. Linearly dependent if and only if one of them is the scalar multiple of the other one. You see, this is it. C1, V2. Okay, so basically this means one vector is what? One vector is a scalar multiple, is a scalar multiple, a scalar multiple of the other one, of the other vector. So it's easy to check. We are going to give you one, we set up two vectors, try to see if we can pull out a factor, a number out of the other ones. If you can do it, in that case, they are linearly dependent. You see, one of them is the proof is like the one that I did for the others. Easily seen, you see, move this one to the other side because the coefficient of the V1 is 1 and 1 is never 0. So this means they are going to be, okay, linearly dependent. Okay, so this is going to be another one. Okay, and I'll give you an example in a minute, but there is something else that if you know it, that would be helpful for us. I want to make a note. And the other one is, if a set of vectors would be given to you, if this set of vectors contain 0 vector, so they are going to be linearly dependent. They cannot be linearly independent, okay? Again, it's a similar results, but very useful. Okay, similar result. That's it. So any set of vectors, any set of vectors, any set of vectors in a vector space, space V that contains 0. That contains 0 vector. Contains the 0 vector. Okay, the 0 vector is linearly dependent. So as soon as you get the 0 in your set, that set cannot be linearly independent. Okay, if you get the 0, this means you can write one of them and the linear combination of the other one. It's very easy to prove. I can prove it for you. See, look at this one. Get a set with the 0. Suppose this is what we got. We got the setup vector. The first one is 0. The second one is v1, v2, v3, up to the vn. Okay. So suppose this is going to be is a setup vector. Is a set of vectors in V. Okay, there you are. What do you want to prove? We want to prove they are dependent. You know that to prove this one, we have to put the C1, C2 to the Cn and prove that at least one of them is going to be, okay, non-zero if you want it to be dependent. If this is going to be the case, you see, let we have a linear combination of this. Okay, what is that? Let we have a C1 times the first vector, 0, a C2, V2, C3, V3, up to the Cn, Vn, to be equal to the 0. Okay, suppose this is going to be the case. So what you want to prove? You want to prove that at least one of these variables is not 0. Because if those scalars are going to be all zeros, this is going to be linearly dependent. So what you can do is, this is it. So if this is going to be the case, now one can assume that, you see, you can assume that the C1 is equal to 1, C2 equal to this, okay, C2 is equal to the 0, C3 equal to the 0, up to the Cn are all 0. You see, look at this one. Because if you substitute these numbers in this equation would satisfy. This equation would satisfy. So you have a linear combination type, if you like, that it's equal to the 0, but one of the coefficients, one of the scalars is not 0. You know that in this case, these sets of vectors are going to be, okay, linearly dependent. So the vectors, the vectors that we talk about it is going to be are dependent, linearly dependent. Okay, so nice results and easy to prove. So if you have a set of vectors that contains 0, that set of vectors cannot be linearly independent. It's always dependent. To prove the dependence, remember, this is the way you prove it. You write this type of linear combination. If you can prove that all the C1, C2 to the Cn are 0, this is going to be independent. But if you can prove that at least one of them is not 0, so this means that vector can be linear combination of the other ones. So in this case, you see this identity is true always if I put C1 equal to 1, because 1 times 0 would be 0. Everything else 0. So I have a linear combination for which one of the variable is non-zero number. So this means these vectors are going to be linearly dependent. Okay, nice result. And you are going to see it. These are going to be a small point, but quite interesting one that we are going to use in future. Okay, so this is the result that you got to know. Now, there are a couple of problems like, so I'm going to give you a sample to be able to take care of it, okay, to see how we apply these type of ideas. that we talk about it. Okay, so example 1 is going to be example. We want to determine if the vectors are going to be dependent, linearly dependent. Okay, so example one is these two vectors. You have a 2, 1, 2, negative 1, 3, and you have a 4, negative 2, 6, and they are in R3. You see the two vectors. Just quickly check to see if one of them is the multiple of the other one. If one of them is a multiple of the other one, so they are dependent on each other. Okay, look at this one. If you multiply this one by 2, you get the other ones. So this is how we're going to answer the question. You say that, oh, this is it. You know, you can call this one V1, V2, or just as is. It doesn't matter. Okay, so if you call this one V1, and if you call this one V2, then you claim that and note that, for example, V2, the second one, is twice of the V1. That's it. So one of them is multiple of the other one, and so they are, and so the vectors, okay, and so vectors are dependent, linearly dependent. Okay, so this is the baby quick. If you cannot, if you cannot find any, if you cannot write it down as a multiple, the first one as a multiple of the other one, of course, in that case, they are going to be linearly independent. Okay, so that's going to be case 1. And you have, a number of them in your book. And the case 2 would like to give you, a polynomial type. So the first vector is 9x minus 6. Okay, and the second vector is 3x minus 2. These are going to be polynomials of degree at most 1 in P1. Okay, again, it's easily seen that, you see, this is it. If you multiply if you factor out the 3, if you like, you get the other ones right away. Okay, so the solution is going to be, you note that again, check to see if one of them is multiple of the other one, which is the case. 9x minus 6 is going to be equal to the factor out the 3, that give it 3x minus 2. That's it. You can call this one, V2, for example, and this is going to be V1. So the vectors are going to be, okay, so the vectors are going to be dependent. Okay, this is how we're going to apply that theorem. Okay, now there are a group of problems that would be of this format. You see, a group of vectors would be given to, then they talk about the kind of applications, a combination of those. You have two nice one in your book, and a nice one in practice quiz. We like these sort of problems. Just give you an idea. Okay, this is it, the example. They start with this one. They say, suppose, you see, suppose the V1, V2, two vectors. Suppose that this is going to be this set of vectors is linearly independent. Okay, they are going to be linearly independent in vector space, vector space V. Okay, so this is what you need, Then they ask you to prove that. Okay, show that. It's going to be 3 vectors, but it's just 2. Show that this is set of vectors, you see. The first one is the v1 plus v2, comma, v1 minus v2, see. So you know that they are linear independent. You want to show that this is also you have a group of these type of problems, okay, is also linearly independent. Okay, so the given one is the v1 and the v2, and this is what you want to prove. You have to focus on that one you want to prove and get the result from here. So it's very standard, and this is the way we're going to solve this type of problems. You want to prove that they are linearly independent, you know that. You write the combination of a C1 and a C2 and show that that C1 and a C2 are going to be 0. Okay, so we're going to suppose that C1 and C2 are scalars such that you have this combination C1 times V1 plus V2 plus C2 times V1 minus V2 is equal to the 0. You see? Now you want to prove that the C1 is equal to the 0 and C2 is equal to the 0. So you assume this, the order of the proof is important. This is the one that you want to prove. So you assume that this is given, then you prove that the C1 is 0 and the C2 is 0. You have to connect it to the original one. A little bit of algebra will do it for you, okay? Algebra expanded, so that gives C1 V1 plus C1 V2 plus C2 V1 minus C2 V2 is equal to the 0. Okay. Now, since your information is about the V1 and V2, put the V1 and V2 together. You see, look at this one. C1 V1 and the C2 V1. You factor out the, okay, factor out the C1 here, or the factor out the V1. If you factor the V1, that gives you C1 plus C2 V1. You see, this is what you got from here. And from the rest, you see these two. If you factor out the V2 here, so that you plus what? Plus C1 minus C2, V2 equal to the 0. Okay, from the given one, we check it. Now, what is this? This is a scalar, linear combination of the V1 and the V2 equal to the 0, but we know that the V1 and V2 are linearly independent. Since V1 and V2 are linearly independent, this coefficient must be 0. Okay, so we say, oh, but this is how you connect. But V1 and V2 are independent. Okay, are independent. So you must have a C1 plus C2 to be equal to the 0. And you must have C1 minus C2 to be equal to the 0. You see? This system of equation, quickly you solve it, you get the C1 and C2 are 0. Okay, you know that. You add them together. That give you 2C1 equal to 0. So the C1 would be 0. And you put it in this one of these equation, C2 would be also 0. That's it. Okay, so we start with a combination of V1 plus V2 and the V1 minus V2, and you prove that the coefficient is 0. So therefore, the vectors V1 plus V2 and V1 minus V2 are going to be independent. Very nice proof. The one that you have in your book and your practice one is there are 3 vectors, U, V, and W. It's the same method. Make sure the order of the proof is important. You want to prove these are going to be linear independent. So you start with a scalar multiplication combination of these two pairs, then you have to factor it to connect to the original one. Original one is V1 and V2. So that's why I factor it so that I get the combination of V1 and the V2. Since I know that they are linearly independent, so this coefficient must be 0. Then that gives me a system of the equation to be able to take care of the C1 and C2. Get to know it. A couple of cases in the practice run that we're going to have. Okay, so these are various examples of the linear independent set. Now, if you take a differential equation, this next one is going to be quite interesting. You see, when we differential equation is going to be an equation that contains the function and its derivative. You see a relationship between the function and relative would be given to, then they ask for the function. In calculus 1 and 2, you just do an easy one by the indefinite integral, okay, or integration, if you like. By integration, so you can get the original function back. But if you consider the set of all those solutions to the given equation in differentiable equation, those sets would be a vector space. When we get the vector space, then we can talk about this type of ideas that we have over here. Okay, so we are going to have vectors, but vectors are going to be functions, differentiable functions. We want to know how we're going to check if those sets of functions would be given to you, how we're going to check if they are going to be linearly dependent or independent. And that's very important for us. We are going to use this idea at the end of the course. And when we get to the next section, if you have some, in calculus, you find so-called special solutions first. Then a linear combination of those special solutions is going to be the one that we are going to be interested in. So we need to prove that those functions are going to be independent. So that's why we have a special formula for it, okay? And would like to give you one question, of course, in your quiz and the next test, in case in future you want to take a differential equation course, okay? Differential equation is basically linear algebra, nothing else. Okay, we have an expression, a tool, they call it the Wronskian. Okay, so we want to know what's going to be the Wronskian. Let's know the name. It's the name of the famous, I think, Polish mathematician who invented this type of idea. I think this is the way we write it down. Wronskian. Okay, Wronskian. The Wronskian is going to be something that we use to prove that the linear independence of functions. Remember, we are in a vector space, so we are on the romantic part. We can use anything we like. We can use matrices, vectors, okay, polynomials, and now we use differential equation. We use a differentiable function. Okay, so the definition that you have to know it if you give me a set of function. So if M1, a little bit of calculus we need, just make sure you know that you refresh your memory, what's the derivative of e to the x? It's just e to the x. Derivative of the sine, cosine. This is all we need. So if f1 equal to the f1 of x, f2 equal to the f2 of x, etc. up to the fn, which is going to be equal to the fn of x. Okay, they are going to be r n minus 1, okay, n minus 1 differentiable function. N minus 1 differentiable functions. N minus 1 means depends how far you go. If you write the 3 function for us, okay, if you write 3 function for us, n is equal to 3. N minus 1 would be 2. 2 times differentiable means you can find the first derivative and the second derivative. Okay, so you start with the function. You differentiate, that give you f prime. You differentiate again, that give you f double prime. So in that case, it is 2 times differentiable. We are going to use only for the 2 case, okay, 2 function or 3 functions. So if you use only two function, so this means your function is only differentiable. Okay, one-time differentiable. But is most of the time it's going to be for three functions. So you have the f prime and the f double prime. Okay. So if these are going to be n minus one differentiable function, let's say on R, on the set of real numbers. Okay, real number, then the Wronskian. Okay, then the Wronskian of these functions. They are going to be vector. You know, there's going to be vector in a space of, in vector space of the differentiable functions. That's it. Because if two functions are going to be differentiable, the sum is also differentiable. And a scalar multiple of a differentiable function is differentiable. So it's a vector space. Okay, then the Wronskian of f1, f2 after the fn is denoted by, okay, it's going to be denoted by this is it, w for Wronskian. And we have the f1, f2 up to the fn. And is defined by, and is going to be defined by, okay, the Wronskian would be defined by a matrix. Okay, this is it, it's going to be n minus 1 by n minus 1 vector, a matrix. You see, this is going to be a determinant of this matrix. You see, determinant. This matrix there, the first row is just the function. f1x, okay, f2x, up to the fn, depends how far you are going to go. Okay, the second part is their derivative, f prime of x. Then we get f prime, f2 prime after the fn prime of x. And then you continue. Since your functions are n minus 1 times differentiable, so this last one would be n minus 1. Okay, f1 and the f2, n minus 1. Then you get to the last one, which is going to be n minus 1 x. Okay, so we find the determinant of this matrix. Okay, so that is going to be the Wronskian. In particular, this is the one that we like. Okay, let's write it down. In particular, the one that we are going to use is going to be if we get two vectors. Okay, so it's going to be two vectors, f1 and f2. So this means they are just differentiable. So it's going to be determinant of the first row is going to be just two functions, f1 of x, and this is f2 of x. In the second row, you have their derivative. Okay, so if you find the determinant, you know that. You cross multiply, so that gives you f1 of x, f2 prime of x, minus, and this is going to be f1 prime of x times the f2 of x. Okay, it's very popular also in calculus 3. And we need it for the 3. And if you have the Wronskian of the f1, f2, and f3, this is going to be the determinant of this matrix that we're going to use it for the problems that we're going to give you. So we have three function. Okay, that's going to be three function. So you have to find the derivative. You have the derivative of the function. Okay. This is going to be the derivative. And then you continue to get to the second derivative. N minus 1. You have three functions, so we go up to the 2. So it's going to be f double prime. Okay, and this is going to be f double prime of x. And this is going to be f double prime. Okay, this is a 3 base 3 matrix, and we can find the Wronskian. Okay, so basically, what we are going to be interested in calculus, these sets of functions are, you see, we have these vectors, and we want to prove that they are linearly independent. So we form a linear combination C1, F1, C2, F2 up to the Cn, Fn equal to the 0. In order to find the C1, C2 to the Cn, we need a system of n equation and variables. So what we do is we differentiate the function, differentiate the equation. We differentiate it again, depends how many times we can do. And then we need the coefficient to be, then we form a system of the equation. This would be a system of the equation. Remember, you have a matrix form of the ax equal to the b. And in order to find the x, you need that matrix to be invertible. And the matrix is going to be invertible if what? If the determinant is not going to be equal to the 0. So that's exactly the same thing that we, are going to do over here. So if this Wronskian is not going to be equal to the 0, this means eventually that system of the equation would have a solution and trivial solution, and then that give you the result. Okay, so I just briefly give you these type of ideas. Use it in nice application of linear algebra for that course differential equation. Okay, so it can be proved. I just okay, I can prove it. What you don't need it. It can be proved that this set of functions f1, f2 up to the fn is going to be independent. Is an independent. Okay, independent set. A set in the vector space. In the vector space. Okay, in the vector space of all, they call it continuously, all continuously differentiable. Continuously means that these functions are differentiable and their derivative is also a continuous function. That's when you say continuous, you know that. If a function is going to be differentiable, the function is continuous. You don't know anything about the f prime. So that's why they call it continuously differentiable function. In the case of the complex numbers, this condition is always true and not for the reals. Okay, if the Wronskian f1, f2 up to the fn is not equal to the 0. Okay, as I told you, if you write it down yourself, okay, C1, F1, C2, F2 to the Cn, Fn, you differentiate it. The first derivative, the second derivative, that give you a matrix equation. A matrix equation, this is going to be a matrix of the coefficient of that equations. Matrix of the coefficient, remember we used to call it A. And we need A to be invertible. A is invertible if if the determinant of this matrix is not equal to the 0. So that's why you end up with the Wronskian. And that's so helpful to solve so-called linear differential equation. Use this one to prove it in that course. Okay, and that's why when some people ask whether they should take the differential equation first or the linear algebra, I usually say differential equation, because differential equation is a classic example of the linear algebra, really, that give a very nice idea. But if you get it at the same time, that would be better, because that's a linear system you want to apply, but you have to know linear algebra first. So that's quite amazing case. Okay, so that's the idea. You just wanted to know it because it's a very classic result, but we give you one easy question on your next quiz, and on the test, we give you a set of function and we want to check it. This is a linear algebra course, it's not calculus course, so we cannot give you, or we are not going to give you any complicated function. The function that we use in science only. Okay, so there you are. We are going to ask you this question. We are going to ask you, for example, show that. Okay, we want to show that this set 1, comma, it's coming from differential equation, so it's either trigonometric function or exponential function, nothing else. You see, set of 3 vectors. We want to prove that they are going to be linearly is linearly independent. Okay, is linearly independent. Okay, so they are a set of function, and we know what to do. These are going to be f1, f2, f3. So you have to form the Wronskian and prove that the Wronskian is not equal to the zero. Okay, it's a tree function. F1, F2, F3. This is going to be, so this is like a solution. Okay, solution is going to be, you don't need it, but I just explain it. You have three function, F1, F2, and the F3. Okay, the F3, which is going to be equal to the e to the 2x. Okay, so the Wronskian for F1, F2, and F3, 2, 3, that's going to be the determinant of this matrix. The first part is going to be F1, F2, and F3. The second part is their derivative, F1 prime, F2 prime, F3 prime. Okay, and the last part is going to be double derivative, second derivative. Okay, this is going to be your second derivative. So this is what you need to do. Okay, you form this matrix first, and then you find the determinant of the matrix. Okay, so substitute is going to be your function. First one is 1, e to the x and e to the 2x. Okay, so there you are. So the first line is going to be the function 1, e to the x, e to the 2x. The second one is the derivative, differentiated. Derivative of 1 is 0. Derivative of e to the x is just e to the x. You know that derivative of e to the 2x would be e to the 2x times u prime. Your prime derivative of the top, so that gives you 2 e to the 2x. Okay, just using this formula to differentiate derivative of e to the x is just e to the x, but derivative of e to the u is going to be u prime e to the u. Okay, we use the chain rule. So we continue the differentiate again. It's going to be 0. This is going to be e to the x. You differentiate this one, e to the 2x. You are going to have another 2, make it to the 4, e to the 2x. Okay, now find the determinant of this matrix, which is very easy. Use this column and just get it right away. So in this case, this is it. This is going to be what? Going to be, the numbers is 1, you don't need to write it down. It's a kind of -1 to the 1 plus 1. And we have the 1 times eliminate. So we get this matrix, if you like. Okay. You get the e to the x. Okay, 2e to the 2x. You can write it down right away. I'll just explain it. So that is what you got to do. Okay, so they're all positive. It's just cross multiply to get the determinant. So that give you 4e to the, okay, e to the 2x times e to the x with the e to the 3x minus the other way around. That give you 2e to the 3x. Okay, so the result would be 2e to the 3x. You know that the exponential function is never 0. This is not 0. Okay, for all x. So that's it. The Wronskian of 1e to the x, e to the 2x is not equal to the 0. And the vectors are, okay, so that's it. The vectors are going to be independent. And with that. Okay, so that's the example of the Wronskian. You have one in your practice one, and you have a couple of them in your book that we already probably we assigned it. So you can get that one too. Okay, so there you are. We are done with the 4.4.3. 4.4 is not bad. But I post another another talk for you about the 4.4. What is 4.4? You see, we study these two types of sets. the sets that we call it the linearly independent. This is linear independent set. And remember, we talked about a spanning set. What was the spanning set? A spanning set is a set that create the vector space for you. You see this one? This is going to be a spanning set of all the solution of this differential equation. So this means any other equation is going to be of the form of C1 times 1 plus C2 e to the x, C3 e to the 2x. If you can find a set that would have these two conditions together, a spanning and linearly independent, this set is going to be called a basis for a vector space. So we are interested in finding this type of basis. It's very dense section 4.4. We just take it a little bit, maybe the first part, to give you a good time to understand this very important section 4.4. Okay, so I post another video for you, and the practice one. And our target is to get to the end of this section 4.4. It would be good for you to keep you going. So I post another one for you, and then a practice one, and then the quiz would be posted by Friday, and then you have by Monday as usual to get it back to the canvas. So any question, just let me know. Okay, have a good one and have a good day and take care.